This is joint work with Patrícia da Costa. She's a PhD student in our graduate program at Federal University of Rio de Janeiro. She's also an assistant professor at the Federal University Fluminense, which is also actually it's in Niterói, nearby city to Rio de Janeiro. I'd like to also thank the organizers for the invitation, especially Adriano and Carlinhos. Before I start my talk, I would like to invite you to become a member of ISBrA if you are already not a member, and also to participate in the ISBrA World Meeting, which will be held in Cancun in July this year. If you haven't seen the program, it's quite interesting. There will be many short courses and very nice talks and many different sessions. Also, if you don't know the graduate program at the Federal University of Rio de Janeiro, if you are an undergrad, I don't think there are undergrads here now, but if you are a lecturer and you would like to visit us, please contact us. We are happy to have you visiting us. And if you are a master's student and consider doing a PhD, consider coming to Rio and living in a wonderful city and having a nice course, I would say. We have many different research areas. Okay, so let's get to the point here. I work on spatio-temporal modeling. Usually I deal with environmental data, and typically environmental data, they require some transformation of the data for you to assume normality of the data. Today I'm going to talk about observed daily mean temperature between March and September. So this is the time of autumn and winter, and in particular, I'm going to focus in the south of Brazil. This is the state of Rio Grande do Sul, and this is the state of Santa Catarina. We have available 176 observations across the days at 21 monitoring sites. So at each of these sites, at each of these crosses, we have a time series of observations. We also have available the altitude at each of these locations and the humidity for each time and location. Usually on spatio-temporal modeling, you are interested at predicting time and interpolating space. You would like to know how temperature behaves in this whole region based on what you have observed in these fixed points in space, and also you would like to predict in time. If we do a very crude exploratory data analysis, these are the box plots of the observations for each time. So these are the distributions, if you will, of the daily mean temperature at all the locations, all the 21 locations. Clearly, I know it's hard to visualize, but apparently there is a trend, as expected, that the temperature decreases across time. If we look at the boxes also, they seem to have like different ranges. If we do the same kind of analysis, but now in space, now we look at the time series that we have at each of the locations, we will observe also that the distributions are kind of different. So maybe a single transformation of the data might not be reasonable. Maybe we should be considering more flexible models. And this is what Patrícia and I have been working at in the past year. If we, now what I did, I took like 6 locations and I have the histograms. If we look at the histograms, it's easier to visualize that they are kind of different. For example, maybe it's reasonable to assume that Porto Alegre, the mean temperature, follows a normal distribution. But also we have to look at these histograms a bit careful, because there is a temporal structure there that is not being taken into account. So what we are going to do here is to propose a spatio-temporal model that allows for different distributions across space and precludes the idea of transformation of the data. There are many different distributions. I will do a very brief literature review. There are many different proposals in the literature on multivariate skewed normal distributions. And actually, in 2004, Kim and Malik, they extended the parameterization of Azzalini and Dalla Valle to account for spatial correlation. However, Gento and Zhang recently showed that this approach by Kim and Monique has some serious identifiability problems, because we know that in the skew normal distribution there is a parameter that accounts for the skewness, and in this approach by Kim and Monique, there is a confound between the skewness and the spatial correlation. However, Zhang and El-Shaarawy in a Environmetrics paper in 2010 proposed a skew normal spatial process, but they assume a single realization. They don't have replicates in time. And actually, if you try, I have another student who has been investigating this model. If you try to estimate the parameters of this model with a single realization, it's quite challenging. It really depends on the number of locations that you have observed. We have been doing some simulations and prior sensitivity to check if we are really able to estimate when we have a single realization. But here we are in a different setup, because at each location we have a time series. So we want to take advantage of the fact that we have replicates at each location. So our aim is to extend the work by Zhang and El-Shaarawy to handle spatial-temporal process. So we assume that CT of S is a stochastic process in discrete time t and location and continuous location S. Usually S is in RP and P equals 2, so S is an index for location, is a vector, usually longitude and latitude in our case, and we decompose our process as the sum of these independent components. I'm going to talk about each of one, but note that we have, if we set sigma S equals 0, we are back to the usual Gaussian process framework. And we would have a Gaussian process, a spatial-temporal process, okay? And so eta t and omega t and epsilon t are independent processes, and T of S is capturing information on covariates that might be available, as is our case. I mentioned in the beginning that we have information on altitude and humidity. And so, actually, sigma S, this skewness parameter will be a function of sigma S, Vt, and tau, actually. And this parameter is in the real line. Zhang and El-Shaarawy, as they have only one replicate, they assume only a single replicate of the process, they assume that sigma S is either greater than 0 or less than 0 to account for right skewness or left skewness. Okay? And as we have replicates, we hope that we are able to learn the sign of skewness as well. So we allow sigma S to be in the real line. Vt and tau are scale parameters, and actually this is measurement error. In the just statistics literature, tau is known as the nut effect, so captures measurement error, the variance of the measurement error. And eta t and omega t are usual Gaussian process, zero-mean Gaussian process with a unit variance. They are independent between them, and they are also mutually independent across time. As I said, MT of S will follow a kind of dynamic linear model structure. This is capturing the temporal story over the region. Okay? So, excuse me. So XT of S can be a vector of covariance, and theta t are the parameters that we allow to change smoothly across time. But note that we assume a common theta t over the whole region. Okay? And here are possible covariates that do not change with time. They are fixed across time, but they might change with space, like altitude. So gamma is capturing the effect of this kind of covariates. Okay? And we allow theta t to evolve smoothly with time, like a dynamic linear model. And W plays an important role here because it captures the variability of this evolution in time. And to give more flexibility, because looking at the box plots, apparently those boxes, the ranges change with time, we also fit models that allow the variance of this process to change with time. But variance is greater than 0, so actually we assume a random walk in the log scale. Okay? There are some interesting properties of this model. For example, Gento and Zhang showed that if we integrate out here, putting it in the notation of our model, if we integrate out, we stack out the observed temperatures in a vector for a particular time, and we integrate out eta t, we don't know the form of this distribution. It doesn't have a closed analytical form, the joint distribution. But if we assume sigma naught here to be diagonal, then we have a certain kind of skew normal distribution. But it can be shown that each of these random variables follow a skew normal distribution with these skewness parameters. So depending on how we assume sigma vt, we can have skewness that vary in space and time. Okay? And also, if we, on the other hand, if we, again, stack the locations for a particular time onto a vector, and we integrate the joint distribution with respect to omega t, we can put the model in the framework of a particular dynamic linear model that now the mean of the observation equation is not zero any longer. This will be very convenient for our MCMC sampler, because I will be able to sample these thetas in a very efficient way. Okay? But as I said, when you are working with spatial-temporal models, your concern is about prediction in time and spatial interpolation. Therefore, the covariance structure that you have in a model plays a very important role, because your spatial interpolation will depend heavily on the covariance structure. And actually, we can obtain different cases of our, the resultant covariance structure that we get depends on how we assume sigma of s and vt. For example, if we fix it, we assume a single sigma for all the locations and a fixed variance, we have a resultant covariance structure that depends only on the Euclidean distance between locations, so it is isotropic, and also we have a single skewness parameter for all the locations, which might be quite restrictive. If we allow sigma to vary with space but fix the variance across time, then we get a non-stationary covariance structure, because now the covariance structure depends on location, and now we allow that each location has its own skewness parameter. And if we want to go and be even more flexible, and we allow V to vary with time, then we have this covariance structure, and now the skewness parameter changes with time and space. So the parameter vector that we have, depend on the assumptions that we make, if we allow sigma to vary with space or V to vary with time, so the dimension of the parameter vector depends on these, and we assume prior independence among the hyperparameters in the model. In particular, when we allow sigma to vary with space, we assume independent normal distribution among them, because remember that sigma is multiplying the absolute value of eta t, and we thought we tried on the beginning to put some correlation structure here, but there was confounding between the two processes, and we were not able to separate the correlation function from one to the other. The scale parameters, they follow usual inverse gamma priors, and I didn't say here, I haven't mentioned it yet, but we are using an exponential correlation function. Therefore, the decay of the correlation with distance is exponential, and phi is the parameter that is measuring this decay. And we allow, actually, we are going to fit models that allow eta t, the Gaussian process eta t, that is allowing the skewness in the distribution, and omega t to have different correlation parameters. Again, this was another restriction that Zhang and EBEB had, because they had only a single realization of the spatial process. They had to assume the same decay parameters for both processes. Okay, and the likelihood function is based on conditional on eta t, is based on a multivariate normal distribution. Again, we integrate out the omega t's to make our life easier. Then in our MCMC sampler, we don't have to sample these parameters, and we get now a covariance matrix that depends on V, the variance, M is the correlation structure plus the nut effect that goes on in the diagonal. And the Fisher distribution following Bayes' theorem is given by this expression. And we have to use, not that we have to, but we use NCMC. And in particular, we have a Gibbs sampling with some steps of the slice sampling and the Metropolis Hastings. The eta t's are quite challenging to sample, and we use a slice sampling. And the theta t's, as I mentioned, because we can put the model in this nice dynamic linear model framework, we use forward filtering, backward sampling, and for the other parameters we use Metropolis Hastings steps. So going back to the data, the covariates that we have available are humidity for each location and time, altitude for each location, and so that component MT has a level that is changing smoothly with time, and we have the effect of humidity, and this effect is also changing with time, okay? And altitude has a fixed effect across time and space. And we fit in 7 different models. We assume a normal distribution for all the time series. Then we assume also a model that first we transform the data, we get the log of the temperature, and we fit the model, and when we perform prediction, we go back to the original scale, and then we are able to compare all the different models. Then M1 assumes that sigma varies with space, so that skewness parameter varies with space, and we allow different correlation parameters for eta t and omega t. Now MA2 is the same as MA1, but we have the same parameters. V, I forgot to put here, but V is fixed in time. MA3 and MA4 assumes that sigma is fixed. The same sigma for all the locations. V again is fixed in time. And MPT is the proposed model that allows everybody to change in space and in time, okay? So what we did, we had this time series with 176 observations at each location. We left out 10 observations from each monitoring site for prediction, and this is the result that we get. I'm showing you the predictions for Porto Alegre, which is the capital of Rio Grande do Sul, and Santa Maria. The crosses are the observed values. The solid lines are the mean of the posterior predictive distribution, and the shaded area is the 95% credible interval based on the log transformed data. But back the prediction, because NCMC allows you to do this, we obtain the prediction in the original scale. And we see that the dashed line here, the red dashed line, are the limits of the 95% credible interval for the model that allows V to vary with time. And we see that it provides a very wide interval. I would expect that in the mean, as it's happening here, the models do not differ much. Usually, from my experience with these spatial-temporal modeling, they really differ in the covariance structure, so they will differ in the ranges of the posterior credible intervals. And if you look close, the models that are providing the shortest, if you will, intervals are those based on sigma varying in space and the decay parameters different for eta and omega, okay? And we used some model comparison criteria. In particular, we used DIC, CRPS by Gnighting and Tillman, by Gnighting and Raftery. And actually, CRPS is very nice because it's based on the predictive distribution. So usually, it's better to be used for prediction, but we also used for the data used to fit the model. So, and these are the mean square error and the mean absolute error, and we also computed these for the 10 observations that we left out from the inference procedure. DIC here we didn't compute because the likelihood has a constant, and I don't think we can compare, we can use DIC to compare when we log transform the data. Maybe I'm wrong here, but I prefer not to put DIC, even if it was here, it was much higher than all the others, but I don't think they are comparable. And so most of the criteria suggest that NA2 is the best model. It's that model that allows sigma to vary with space. And the PD, the component, the DSC component that penalizes for the model, seems to be very consistent. These models here, they have Vt fixed, V is the same for all time t, and sigma is the same. And we see that PD is very low here, whereas in these models it's quite high. But in terms of fitting, these models apparently do not provide the best fittings. Okay? So I'm going to show you the summary of the posterior distribution of some of the parameters in the model. I always like to look and interpret what is the parameters are telling us. For example, this is the level of the across time for all locations. And as expected, because we have temperatures in autumn and winter, the mean level is decreasing. And apparently, the models are not very sensitive to the structure that we assume for those two latent components, zeta t and omega t, if sigma is varying with space or v varying with time. They seem to be not sensitive to this, okay, because the posterior summaries are very similar. And here is the effect of humidity on the mean temperature, which is always negative. And these are the posterior summaries of gamma, the effect, the coefficient of altitude. As expected, the higher you get, the lower the temperature, okay? And again, I'm not sure the log transformed model should be in here because they are in different scales, so it doesn't make much sense to compare them. But at least all of them are negative, and we see that NA1 and NA2, which according to the criteria were the best models, they provide similar values. But as I said, it would be nice because if sigma is 0, we are back to the usual Gaussian process. And for example, if you remember when we looked at the histogram of Porto Alegre, it suggested, we have to remember that there we had correlation in time, but it suggested that maybe a normal distribution would be suitable. And if we look at sigma of Porto Alegre, 0 is included in the 95% credible interval. When the black and the red is because you either assume different decay parameters in the correlation function of eta t and omega t, or you allow them to be the same, it's just this. But sigma is always varying across the space. And again, it seems reasonable that we allow sigma to be in the real line, because for some cities sigma is positive, for others it's negative, suggesting either left or right skewness. Usually in spatial statistics we look at this decay parameter to understand how the correlation is behaving, but in these models it's kind of tricky because we have these two Gaussian processes. The correlation structure is a bit more complex, and what we did for each distance, we estimated the correlation among the points. I don't know why Patricia cut this plot, because I know the largest correlation that we have in the data is nearly 800 kilometers. So this goes much further, but as we see, the decay is very smooth. And as I said before, if we allow sigma to vary its space, we get an anisotropic correlation function. For a given distance, the correlations are different, as expected. Okay? But what we see is that we have, if we were to draw a surface of these processes, we would expect a very smooth surface because the correlation decays very slow as distance increases. These are the summaries of the variances. And this is the model that allows V to vary with time. And we see that apparently the variance is increasing as time goes by. But I confess that I'm still not understanding well. For example, I would not expect that this model provided very wide credible intervals for the predictions. So maybe we have to go back and see our computations. But one interesting point is tau. Tau is the nugget effect. Is the component, is the parameter of the model that is capturing whatever is left after you account for the skewness, the spatial, and the temporal structure. And what is interesting is that if you assume normality, the tau has, well, it's overlapping with NA3 and NA4, which assumes sigma fixed across the space. But we see that when we allow sigma to vary with space, or the variance, they provide the lowest values of tau, suggesting that whatever is left has less structure than the normal model. And again, the log normal model should not be here because it's not fair to make this comparison because it's in a different scale. But if we look at these are the observed and fitted values observed in red, and the dotted lines represent the limits of the 95% predictive distribution. As expected, when we are modeling daily processes, they have a lot of noise, yeah, as you can see from the red lines. And our estimates are the black ones. For most of the series, I'm showing just 4 locations. Our estimated value, the observed series are within our 95% credible intervals. But we can improve this. I haven't mentioned anything about W, that variance that captures the evolution in time of the parameters of the dynamic linear model. We are not estimating W, we are using discounting factor, because if we estimate W, then we fit the data perfectly. Because there is an identifiability problem between all these variances going together. So that's why we opted to use discount factor, which is quite usual in the dynamic linear model literature. But maybe we have to play around a bit with the values of this discount factor. Maybe we are giving very high values. We could give lower values. Maybe, I don't know. We have to explore. Just to wrap up then, our proposed model precludes the use of a transformation of the data to attain normality. It allows for different distributions across locations. It might result in a non-stationary covariance structure. Predicted values of future observations obtained under the transformed data result in a wider credible interval, so maybe this suggests that it's not a good idea to transform the data. But again, the VT, the model that allows the variance was even wider. We have to check this. This is work in progress. I forgot to mention this when I was introducing myself. And we also have to investigate the behavior of this spatial interpolation. We were doing this, but again, we are double-checking our codes. So I'd like to finish by thanking CNPq, and especially CAPES. Patricia benefited from a scholarship from CAPES for her PhD. And again, thank you very much for your attention.